So yeah, today, start off. I'm Alex Boote. I'm the Product and Innovation Manager at ARC Building Solution, and we're doing this webinar today to essentially look at how we can address damp and mould at the Eaves Junction. So, as a bit of an overview of what we're going to be doing, I'm going to do a quick intro to ARC for those of you who aren't familiar. I'll do a bit more of an intro about myself. Then I'll be going into why correctly insulating homes is so important. So that's going to be looking a little bit at the U value and then looking at thermal bridges as well. Looking at some of the variations between homes and what the key variables are that we need to consider when insulating, specifically that Eaves Junction. Then I'm actually going to sort of dip into some thermal and ventilation sort of science basics, not too much at all, real light touch. Talk about how that is going to be all relevant to past 2035 projects, and then why the Retrofit Eaves Insulator essentially addresses all of those issues that we've sort of touched on. So it's sort of a long setup really for the conclusion of the Retrofit Eaves Insulator, and then literally 2 lines on what's next. As you know, sort of innovation. Sometimes we've got to be a little bit cautious about talking about it too much, but in terms of questions and stuff, you guys should be able to put things into the chat. I've never done one of these where I can't speak to you directly and people can't unmute themselves, so if you put it in the chat, I'll try and keep an eye on it. It's a tiny box in the corner of my screen there, so hopefully I'll see it. If not, Jake, our marketing manager, is going to be keeping an eye on that. So he may nudge me at the end for any sort of particularly pertinent questions that come up. Otherwise, just get in touch with us. We've got a solid team here that are able to deal with all sort of inquiries. So yeah, just reach out and we'll be able to get you sorted. So first off, as I say, we'll go into our building solutions and won't labour the point too much. Traditionally, our stock has laid in cavity fire barriers and cavity closers. So sort of everything relevant to approved document B, that's been our heritage. So you can see there over 15 years of that. So as many of you will know, a lot of people on the attendees list sort of recognise as previous customers. So you know how effective we are in that realm. And now we're sort of becoming experts in insulation solutions. So specifically, many of you will know about the Eaves Insulator. So that's for new build projects. But we've developed a product, as we'll see through this, specifically for a retrofit scenario. So that comes with its own complications and its own awkward elements, so that's where sort of our expertise is leaning towards now, specifically with myself, but we're very much an R&D oriented organization, and that sort of, I think, was in the DNA of ARC. The original founders and the technical director, they're very much concentrating on that innovation and that innovation mindset, but I was brought in to formalize that process, to build a new product development process. So in terms of my background and sort of why I've sort of got a leg to stand on, I guess, my undergraduate degrees in mechanical engineering, got that at Newcastle University. Then I went on to do a biomechanical engineering PhD. So that was focused primarily on cemented total heat replacements. So if you ever need one of those, reach out to me as well. I'm sure I'll be able to give you a bit of advice. But as part of that, there was a lot of thermal and fluid simulation elements and considering that side of things, as well as sort of that, I guess, innovation and research underpinning and working with materials. So once I'd done the PhD, was sort of coming out of COVID, and I'd got bored of working in a lab, and unlike many other PhD students, I quite like other people. So I wanted to get out into industry and work with a company that is wanting to sort of have that innovative mindset. So I started a knowledge transfer partnership. I'm not sure if you've ever heard of them. If not, I'd thoroughly recommend you do a bit of research into those. It's very, very useful. for companies that are wanting to implement some sort of innovative change, whether that's a technology or a process. There's also management KTPs. So this webinar is not about that. Don't worry. I could talk about them forever, but I'll refrain. But essentially, that ended with us in very tight collaboration with Leeds Beckett University, and through that we developed this product, the Retrofit Eaves Insulator. And now I'm operating as the product and innovation manager, overseeing that those technical elements. As you can see there, I ended up with a patent in a surgical device from my PhD, and we've already developed two now in my time at ARC through that new product development process. So we practice what we preach, essentially. We make sure that we're sort of looking at ideas, coming up with innovative solutions, and then converting those into products. And the Retrofit Eaves Insulator is a great example of that. So in terms of why insulating homes is vital, I guess those first three is what we can look at. So obviously, the better we insulate a home, the less likely it is for energy to be able to escape. So that's going to reduce the sort of carbon burden of that home and of the occupants of that home on the planet. So going towards that net zero goal and looking to be more sustainable. Some would say the main benefit, rather than that, is actually the cost of living. So making sure that those bills are cheaper, having a better insulated home is always better than that. One of the lecturers at Leeds Beckett used to say, it's like putting a big old quilt, like a big old duvet over something. You're going to have a lot easier time heating that than you are a shed. And finally, they're warmer homes. That's something that I don't think is mentioned enough. Really important for tenants. I've lived in homes where I can see my own breath, and it's not very nice. But then that's where that bottom one, that damp and mold, sort of fits into the list. But I don't think it often or historically has been the primary reason for insulating a home. And in fact, we'll go into it a little bit more detail soon, but it actually should be one of the prime reasons why we need to get that first word correct. So I'm not sure if you guys can see my pointer, but correctly, it's so vital. There are so many situations where we've gone in, insulated a house, and we've ended up making this damp and mold problem tons worse by insulating it, which to a tenant, they've gone through all that disruption just to end up with a worse home. It's not very good. So this is where we've all decided, yeah, it's good, we should insulate homes. I think fabric first has given way slightly to looking at power generation, but still it's near the top of that agenda of things that we need to consider for net zero and also for improving the UK housing stock. But the UK housing stock is incredibly varied, incredibly frustratingly so. One of our proud things is that we've got such an old country, but that makes it very awkward for people who are trying to upgrade their housing stocks for tenants, or people move into homes and end up with a project that's far larger than they might have considered at the start. So that's a problem for the people who are living in them and who own those homes, but it's also a problem for us as manufacturers. When we try and come up with solutions and with testing, we want to create a situation for you guys and for installers where it's easy to specify, it's easy to install. The UK housing stock makes that very difficult. If you look here for the variations from home to home, and each of these things are relevant for retrofitting that insulation in the eaves. So you can see terraced semi-detached houses primarily are the main properties with pitched roofs, flats maybe on the top floor. But that can make a difference to how we're insulating, especially at the very edge, sort of rafter spacing. If you look here, pitched and flat roofs, the pitch of the roof is something that varies hugely. You can have bungalows, very, very small sloping, 10 degrees or up, and also up to where you've seen pictures of roofs where it's almost vertical. Rafter dimensions and spacing, that is probably the thing that is most difficult for insulating the loft and for the eaves junction. And it's also the thing that might vary most historically. I've seen houses with rafter spacing of 300 millimeters, 30 centimeters is tiny. And then the dimensions of the rafters have changed so much. A lot of it's to do with timber availability. And now, if you look at, I quite like wood. If you look at a cross section of an old bit of construction timber and a modern bit, you can see how many more years it's taken to grow the old stock. So it's a lot stronger. It meant you could have smaller rafters. So now, also with modern methods of construction, we've got things like trusses. So it's the load bearing capability has changed so much, and the rafter dimensions and spacings are one of the things that changes significantly with that through time. In terms of your insulation levels, cavity walls, as you know, partial, full fill, blown fibre, all affect what we need to consider when we're retrofitting. Solid wall, whether it's internal or external insulation, affects these details. And on that, actually, the reason why it affects it so much is because each detail typically needs to be simulated itself to get the psi value of it, unless it's a typical detail. So all of these things need to be accounted for in that thermal model, which it can be quite exhaustive, to be honest. And then finally, at the end there, you've got the cold loft or the warm loft. Obviously, in the cold loft, it's pretty clear you're going to need that loft insulation, and you're going to need the eaves to be insulated. But on the other side, that warm loft, a lot of room in roofs, they can often have sort of the fake walls. That means that you've still got your exposed eaves detail. So even with the wall loft, this product can be installed. I recently went to a property a few weeks ago, which had exactly that situation. It had been sort of put plasterboard up, which is inadvisable because it wasn't insulated, but plasterboard up and round, but then the eaves were still exposed, creating a huge thermal bridge there. Let's do a quick run through of the U value then. I think it's useful, even if you do come from sort of an insulation background, sort of reconsider these things. And usually I'd be doing this on a tablet or something. But we can see here it's pretty simple. It's how easily heat can pass through a surface. A lower U value means it's more difficult for heat to pass through. And these are the units, watts per meter square Kelvin. So watts is the amount of energy that passes through in a second. Meters squared is the area that the heat will be passing through. And Kelvin, that sort of should be delta Kelvin, because it considers the difference in temperature from the inside to the outside, or whatever the energy, the heat will be passing through. And this is the bit where I've sort of got the pencil out, I guess, is calculated using the reciprocal of the sum of the thermal resistances of individual building elements. Now, again, a lot of you guys will know this, but basically, if you're calculating the U value, it's 1 over R1, 1 over R2. And each of these R's is representative of a different material. So if you've got, say, a pretty typical block and brick wall, you might have plasterboard, dot and dab onto block with a cavity. Let's assume it's empty, and then a brick wall on the outside. So then we'd have the resistance of the plasterboard, the resistance of the dot and dab area, which can be accounted for in simulations, so on and so forth, all added up. And the reason why I wanted to bring this up is because this R value is the thickness of the material divided by the lambda value. So that's the thermal conductivity, how easily heat can pass through that material. So we've got two choices there. Well, I guess three choices at the bottom. You can either add more layers, so you add more of these. That can make it more difficult for heat to pass through, or you can increase the thickness, or you can use a lower lambda value, so it's more difficult for heat to pass through. All that being said, that's very relevant for your sort of flat surfaces, and also when you get onto strange things like skeelings, which we'll revisit in a bit. We can't use the U value at the Eaves Junction because it's not a surface detail, it's a thermal bridge. The BRE defined that as an area of a building construction which has significantly higher heat transfer than the surrounding materials. So that could be a point in a construction such as at the eaves, which is, because it's more difficult to insulate, we end up with the thermal bridge there. And the thermal bridge has a couple of effects. And those effects can be sort of summarized or I guess captured, always partially because it's difficult to perfectly describe something. But the psi value is a measure of how much heat is lost through a specific junction relative to its length. So that's almost a thermal bridge inversion of the U value. The only difference is that it's watts per meter Kelvin rather than meter square Kelvin. So it's still looking at that rate of heat transfer through that junction relative to its length and also the temperature difference. But I find psi value, it's one of those numbers that's a little bit arbitrary in a way. You can't look at it and be sort of sure exactly what it means, yet told we need to reach a certain psi value. But to understand that and sort of feel what it means is more difficult. But the temperature factor, which is the more relevant value for mold development, it's a lot easier to sort of feel. It's essentially the ratio of the coldest space on the internal surface divided by the difference in temperature from internal to external. Now there's a little bit more nuance to that. But if, say, we have a room and it's 20 degrees inside, 0 degrees outside, and the coldest spot on the internal surface is 10 degrees, that means we can do 10 divided by 20, which is the difference. So then we get a temperature factor of 0.5, and that's not a very well performing thermal bridge. And with perfect insulation, the temperature factor would be 1 because it would be as hot inside as it was the difference between inside and outside. So those are good ways to sort of summarize the point of a thermal bridge and how well it performs. In terms of the temperature factor, we're looking for something in the realm of 0.7 to 0.8. I think 0.75 is really what people go for, but the literature, there's a few different thoughts around that. But the reason why that temperature factor is so important is because of surface condensation. The main problem with thermal bridging, we brought up why it's important to insulate homes earlier. The most important thing with thermal bridging is the fact that we get a cold spot that surface temperature factor describes. And with that cold spot, we're likely to see surface condensation. Now, again, you guys might be very well aware of this and doesn't need explaining to you, but I find it quite interesting to think about is essentially what happens is hot air can hold more water than cold air. That's why you can go to places in sort of a rainforest or somewhere where it's really warm and the humidity is stifling, but it doesn't happen very frequently in England. It's never that sort of warm enough for the air to hold enough water. So when we're putting that into context of warm and cold surfaces, you can think of a beer bottle on a really hot day. You'll notice that you get condensation on the outside, and that's what it is. There's lots of moisture in the air sort of floating around because it's nice warm air. As soon as the air gets close to the beer bottle, the water that's been held in the air, it can't hold as much anymore near there, so then the water starts to condense on the beer bottle. It's the exact same thing in a shower room or just any room in the house. You've got it's winter, it's really nice and cozy, you've got it all nice and warm, everyone's breathing out moisture. So I was doing some calculations earlier, and I think it's 142 litres per year that we exhale in terms of moisture. And if you think about that amount of moisture in the air, when it's warm and there's not much ventilation, you've got all your windows closed, so all this air is just floating around, all this moisture is just floating around. And then if you've got a cold spot, a bad thermal bridge, that moist air is going to condense on that surface. Additionally to that, we breathe in a lot of, obviously, we're in an ecosystem ourselves. We've got lots of bacteria, lots of mold just in us naturally, as is normal. And that is also coming out and condensing and being part of what is ending up at those cold spots. So really, I'm trying to make it a little bit more real, is why we don't want cold spots on those internal surfaces. And this is a prime example. This is always comes to my mind. So this was a house that we went to a year or so ago now, and just doing some thermal imaging, some thermography on this house. And this person had really bad mold on those surfaces. This is in a bathroom, and you can see the cold spots coming in around a foot from the wall plate, and you can see the rafters and everything. That is fascinating. But this is a bungalow, and this is a bathroom, so they had a really low pitch. So you can imagine you got your low pitch, and surprisingly, this house maintained ventilation in the loft, and they had stepped insulation. It came up and across, and then another layer was up and across. So then this is the area that has no insulation at all, and you can see it there. It's clear as day. This person, every year, they were scrubbing this off using anti-mold paint, and every single winter it'd come back when it started to be cold enough outside again for mold to build up. So he came in and said, yeah, no worries, pretty typical. This is exactly what we expected. And we installed the Retrofit Eaves Insulator, and you can see there, it's coming right up to that wall. You've got some shape effects here with at the very corner. They're just sort of imaging phenomena. But you can see here how much better it's being insulated. It's coming all the way up. Everything's nice and warm. You're not going to get as much condensation there as you are in other locations. One more point I just wanted to sort of land on there is with the thermal bridging and the cold spots, the reason why we get worse damp and mold after a retrofit job, if the thermal bridges, such as the eaves, aren't treated properly, is because if you imagine all of the room is cold, all of the moisture that's in the air is going to condense equally on all of those surfaces. But if you heat up all of those walls and ceilings, but then you've got a tiny strip, like here, a tiny strip of cold spot, all of your moisture is going to condense on that one spot, and it's going to be dripping. It's going to be horrible. So that's why we can often see it gets worse post retrofit. So that's the thermal bridging elements to this. And the ventilation there, I sort of touched on it with the surprising case study there. We need to consider ventilation in all retrofit, especially past 2035 projects. But the Eaves Insulator specifically deals with ventilation in the loft. So my surprise in this scenario was they left this gap open. It was an Eaves ventilated property and a cold loft, and they kept this open, which caused a thermal bridging problem, but they didn't have a ventilation problem. What can happen if people stuff the insulation deep into that the eaves, thinking, "Oh yeah, I'm solving this. I've been thinking about it." There's not going to be any thermal bridging. We might end up blocking that ventilation path, which means that the loft might sort of sweat. So all of that moisture I was talking about earlier, if that's allowed to penetrate through the loft hatch into the loft, it's going to condense on there. It's going to cause mold. It's going to cause rafter rot. So if there's any belongings there, they might be ruined, and it can cause significant structural damage. We've seen that before. So it's imperative that we maintain that ventilation whilst also making sure that we insulate the junction. It's quite a difficult balance to achieve, really. Here you can see it goes into a little bit NHBC guidance, looking at the ventilation requirements. There are very many different types of ventilation. Often it's difficult to sort of know which one a house is using unless you get up there. But it's good to maintain that Eaves ventilation path if you're unsure. It's frequently ventilated through that strategy. So another element that many of you guys will be very familiar is past 2035. And in there, you need to consider all elements of a retrofit, so including your ventilation, your insulation, thermal bridging, warming, overheating, cooling. And this sort of summarizes it, really. the Retrofit Eaves Insulator considers those things. Simply stuffing insulation into that cavity doesn't really work. There must be a ventilation strategy as well to get that government funding. And we've got to make sure that properties at high risk of structural damage, we need to consider it, especially in there. So there we go. That sort of summarizes the question, the setup, sort of into the next phase now. With that eaves being so important and such a known problem detail, it's difficult to install, insulate and ventilate. What do? You've guessed it. So it's the ARC Retrofit Eaves Insulator. I can see it's very simple. This is an accurate render of the product. It's it's ventilation tray, which and bagged insulation. These two things come together, so there's no messing around. It's really easy to install. It considers your insulation and your ventilation, and it's provable. You can point to a piece of paper that says, yeah, this product we are considering ventilation and insulation. So it's suitable for the past 2035 projects. It's a very simple solution to that complex problem, that painting I tried to, the picture I painted there. You can use it with any roof pitch above 10 degrees, so we're removing that element of variability of the housing stock. It's very easy to install, so it cuts down on the labour cost, and it's ready for use, self-contained. The only element we need to know, and you need to measure, is the distance between the rafter, so that rafter spacing. You can't avoid that. We want this insulation to fit in there nicely. We've got a variety of products that capture a range, and we'll see that in a moment. But yeah, we need to sort of be aware of that. So revisiting these thermal images, you can see how it works and fits in with how this is working here. It goes straight over that wall plate, avoiding that thermal bridge. And that's the effect of it. In terms of actual numbers, again, as I say, you've got to simulate your own details to be sure. But these two are when you install no insulation and loft wall insulation, looking at the psi value. So that's just, as I said earlier, the measure of how bad the thermal bridging is. And you can see that massive drop there, over 50% reduction in the psi value. And that's the only difference there is installing that Eaves insulator. You see further drops. This was based on a real case study. So this isn't universal, but this is worst case scenario, to be honest with you. Here you can see we've added soffit insulation. That's the only difference between these two. Before, in this simulation, there was only wall up to that soffit. If we insulate above the soffit, we get another huge drop, again, over 100%, which is the more typical version. And then finally, if you imagine if you achieve continuous insulation, so your loft insulation and your wall insulation is continuous. That's the dream scenario. We've got a product called the Eaves Insulator that does that in new builds, which is sort of tried and tested. If you achieve that, that's a perfect scenario. Also here you see again the same simulation, so no insulation, wall and loft, and then as soon as you have the Eaves insulation, the temperature factor shoots up 0.2. So it's massive, and that's at least we've sort of made these universal. But you see that huge jump, and then we get another huge jump with the continuous insulation. So if you're considering a loft insulation project or a loft and wall insulation project, it really pays dividends to consider the Retrofit Eaves Insulator to make sure that you're maintaining that ventilation in the loft, and also getting this huge jump in temperature factor and huge drop in psi value. So coming back to the render, sort of highlighting some of the key elements, we get a far better insulated junction, easier to install, the ventilation's maintained, and you can see you can install your loft insulation up to the back here, and you've got a perfectly insulated roof loft space. This is harking back to what I was talking about, the rafter gap. We only need to know it in these increments, so we just need to know what band your property is in, what the gap between the rafters is, and then we can recommend a product. So you see here we've got 5 products, and that should cover all sizes in the UK. I'll just note on that last one, this S and L, they correspond to width of ventilation tray. So as part of sort of NHBC guidance and in terms of retrofit, you've got to make sure there's enough ventilation per meter. So that depends on the house type, but this S&L makes sure that all house types and ventilation requirements are covered by this one product. Again, it was trying to condense that huge housing stock diversity and manage to come up with a solution that solves as much as possible and is as little as products. Here you can see our installation instructions. It's super easy. Done it thousands of times now. It comes flat. This tray actually sort of comes under here and then folds up here. It'll come flat, and then all you need to do is fold it at half. It's got an active hinge here, which means that it will be pushing back. You can press the bag so that all of the air comes out of the insulation, and then you push it into that eaves detail. As the air is sucked back into the bag, it'll recover, opening up, and then these ventilation ridges will be flat against the roof, the underside of the roof membrane, ensuring that your ventilation is perfect. Then you can just build up your loft insulation as required behind this to the height that you've specified. So as important as all of that is when to use it. Obviously in a cold loft or a warm loft which has exposed eaves, specifically when you have no access over the wall plate. That might be because the wall plate is protruding slightly. It might be that it's notched rafters. It might be that you've got a noggin in the way there that you can't get over. It might be that it's 1 brick thick, so your insulation can't go over that. So it's when there's no access over that wall plate. Additionally, if there's a concern about sufficient ventilation and insulation at the detail, if you want to have it so it's signed off, yeah, great, you've considered those things. This is the solution for it, because it is a complex problem at the end of the day. It's a difficult detail, and that's why we get so many issues with it, even in properties that have been retrofit. But again, as I sort of started this whole thing off with, if you're unsure, get in touch. We've got a great team here. As you can tell, hopefully, we sort of know all the ins and outs of this issue and these problems. So we can definitely help you with whatever your situation is. What's to come? I think I teased this a little bit by bringing up the scaling earlier, but we're looking at a product that will be suitable for going over the wall plate. At the moment, there's nothing on the market that can do this at all. As well, there's nothing in the market that can do what the Retrofit Eaves Insulator can do. But as ever, I'm an innovator looking at the next thing. And this is as well a potential solution for the scaling, which has just plagued people for years and years and years. And they're still building houses with scaling, and I can't believe it. But we'll soon have a product which can address that issue as well. So if you've got any properties with that detail in the coming months, we should be able to support you in that as well. So please reach out and we'll make sure you're sort of included in any communications. So in terms of questions, I've seen that Paul sent one through. Is the insulator suitable with old sarking roof felts? Yeah, it should be sound. Obviously, one of the potential problems with some older roofs is you get a lot of sag in the roof membrane. So if it can't sag too much, that should be fine. But yeah, old sarking roof felts as well. That should be no issue at all. It covers everything in terms of that. Is there anything else that people want to shoot over? As I say, if not, feel free to reach out and we'll support you in anything you need one-on-one. Great stuff. All right then. Well, I'll assume for the moment there's nothing else to answer. So yeah, fingers crossed. Reach out and hopefully speak to you in the coming weeks and months. All right. Cheers, guys. Bye bye.